Hello, my name is Bradley Alicea. I'll be presenting on behalf of my co-authors Brian McCorkle, Hussein Ather, Himanshu Shogul, and Jesse Parent. This talk is titled Open Source Sustainability, an Agent-Based Cybernetic Approach, and we're from the Orthogonal Research and Education Laboratory. So the motivating question for this talk is, how do you keep an open source community both active and encourage virtuous behaviors? So there have been a number of attempts aside from ourselves to do this. One of them is Yielding Open Source Health Information, or YOSHI. Another is SourceCred. Another is the Financially Stable and Free Open Source Communities Initiative, Git Compare. And then there's Open Source Software Health and Sustainability, or Augur. And so a lot of these methods, they measure contributions through a GitHub repository or something like that to an open source community. And then they monitor this for changes and fluctuations. And then that's how they distinguish virtuous behaviors from non-virtuous behaviors. So the focus is on optimizing the endpoint of the community, which is contributions. And so how do contributions and working open, which isn't just like open source code, how do these activities become self-sustaining? And so one answer is to look more broadly at the participatory governance. So there are a lot of things going on in communities, and especially in our community, that are different from just measuring GitHub commits or other types of open source contributions directly. And those include open access publishing, forum management, generative contributions, such as things that come from the software that you make, and then usability and data analyses. So all of these things can be measured and accounted for, but you have to do this not just by bean counting, not just by looking at the numbers of commits or things like that, but you have to have sort of a systems view. And so this is where we propose a cybernetic approach to this. So the first thing we did was we developed 3 adversarial but interrelated approaches, and then we mapped them to this cybernetic approach. So the first one is the active inference model, and this is an attempt to model the theory of mind and collective behavior. The second is a reinforcement learning model, which involves looking at positive behavioral feedback and its effects on the community. And the third is Big Five cybernetic personality theory, and that looks at the interactions between agents over time. And so to do this, we implemented agent-based models for these 3 projects. We actually developed this over the course of a summer and a fall. The summer and fall of last year, we did this virtually by meeting and giving demos and discussing the sort of the implications of all this. And we have a code repository with all these models in them, which is now available. And so the first thing we want to talk about is active inference. And so this is with a particular focus on theory of mind, or knowing what you know and feeling what you feel. And so this is where the agent tries to infer the mental state of other agents, and other agents try to infer your state, and you try to coordinate your behaviors. So this collective active inference project, this was done by Brian McCorkle. This uses Interactively's PYMDP package, the Markov Decision Processes in Python package. It's a variant of DEC-POMD, or POMDP, which is multi-agent partially observable Markov decision processes. This is a type of modeling where you treat the community as the sort of model of the mind as a Markov decision process, and you have partially observable states, which are the things you think other people are thinking, and you have a multi-agent model. So all of this is developed in a single agent and then applied to an agent-based model where you have agents interacting. And so this serves as a multi-arm bandit for an agent to maximize and exploit trade-off. In other words, the agent has to make a decision. Do I want to contribute to this community or not? And it has to, of course, get information from other agents. It has to figure out what's going on in the community. And so what are the opportunities to either explore or exploit those opportunities? We can also use active inference to maximize the trade-off for each agent. So there's this variational free energy, which is minimized, and there's a maximal payoff with respect to involvement. You also have Bayesian inference, which allows the agent to update their beliefs about the situation in the community at the current time. And then over time, those beliefs kind of converge across agents and then provide these sustainable behaviors. So this is an example of the belief distribution over 9 time points. we have a bunch of beliefs in the first time point, and it converges to a single belief at the last time point. And this is how this process allows you to uh, sort of converge upon the most virtuous or the most sustainable behaviors. And so this is a single agent's architecture. So the agent believes certain things about the world, and then the agents converge upon the same beliefs given similar environmental conditions. So the environment is down below. There are these sensory states from the environment. The agent receives them. They compare that against a set of internal belief states, and they have this target encoding for this virtuous state. And then they emit active states, which is their external behavior. And so they try to optimize this with respect to the target encoding and the currently active states out in the environment. And so the Markov blanket is this boundary around the system. It allows us to have a set of belief states within the system's boundaries, which is the mind of the agent. The agent emits a set of active states to other agents, which is this outward behavior at time t. So it could be something like a set of GitHub commits, but we're only treating that as part of the agent's behavior. The internal beliefs become consistent with respect to this target encoding. So this implies that you can have community standards that can enforce certain behaviors, and that the agent will, if given the right incentives, align their beliefs with the community standards. And then the influence of sensory states from the environment. So sensory states are maybe things like economic incentives or time incentives or things like that. And so they're aligned with respect to those as well. And so the idea is to have a bunch of agents, each of these agents with the same sort of architecture, interacting with one another in an agent-based model. And so if every agent believes similar positive things about their open source community environment, then collective behaviors will converge to a virtuous equilibrium. So if all of these agents are on the same track, so to speak, if their beliefs converge to a single set of beliefs which are virtuous and positive, then you end up with these virtuous and positive outcomes. And remember, this is just a simulation, but the idea is that we can simulate particular outcomes, we can parameterize these kind of interactions so that someone running a community could take that information, map those parameters to their own community, and figure out what they need to do to match what these simulations are telling them. So we have something called the open source development community model, which is a special case of this, which is specialized for open source communities because the current, the main implementation is just looking at collective behavior generally, and it's not really specific to an open source community. But the open source development community model is specific to some of these coordinating mechanisms that are specific to open source communities, such as onboarding and community standards. And the boundaries and locations of the individual agents can be adjusted to the size of overall contributions. So you could measure repo size, your agent could respond to repo size, but that's not equivalent to the size of other contribution types. There are many things in the environment that the agent is taking into account, not just specific measures or metrics, but there are other things as well. And it can be adapted to a wide variety of contribution types. So given specialization of the open source development community model, you can incorporate different types of metrics or intangible things that can help with this optimization process. And so convergent beliefs drive collective behavior. The open source development community model is particularly well suited to mediating the free rider problem, which is where people try to benefit from a system without contributing to it. Now, the second project, or the second approach, is this multi-agent reinforcement learning model. And so this is an example of multi-agent reinforcement learning. You have a reinforcement learning model, which is reinforcing virtuous behaviors. You have a series of policies to choose from, and you pick the best policy, and that gets reinforced if there's a sufficient reward for your efforts. And this is just doing this across multiple agents. So you can see an example here. And this is being adapted to this same idea of open source communities and sort of promoting virtuous behaviors with respect to maintenance and respect to other things like that. And so this is an example of our agent-based model where you have the community experiences, the community participant. There's an agent that interacts with its environment, which is the community, and they get this set of policies that are possible. They have to select from those policies, and so then we get this promotion of the better behaviors, hopefully, because they're promoted by rewards, or there's a reward signal that gets interpreted by the agent as to do more of this thing. And so this is actually a spatially explicit model. So we can actually model the community as a spatially explicit entity that could involve different time zones, or different types of leadership roles or different types of maintenance roles, and model those as spatially explicit phenomena. So we can do these sort of things to improve the model as well. So virtuous behaviors are amplified by rewarding positive interactions. So that it exploits the parallelism of this agent-based model approach, but the learning aspect of the reinforcement learning approach. And so we use Q-learning as a community building guide. We take temporal differences, we calculate a learning rate, and then we take the current value and predict an updated value. So all these things come from the interactions of the agent with other agents in the community, as well as the environment of the community itself. And these different policies, there's a temporal difference in their reward structure, and then you get a learning rate, so the agent's learning, and then you update the current value of Q. And so we can look at differences over time. What is the maximal value of a learned behavior when compared with the current behavior? So if you're learning that being a maintainer of your repository is a good behavior, you keep reinforcing that until maybe you yourself become a maintainer. Or you may find that expertise is valued in your community. So you may optimize that reward with respect to expertise, and you take on a leadership role in that community. And so we can also look at the learning rate and think about how often facilitatory behaviors are required. So, these kind of facilitatory behaviors, as I just mentioned, what is their acquisition rate? So is it common or is it uncommon? And this actually leads us to a broader set of questions related to cultural evolution in open source communities. So the culture of an open source community seems pretty intangible, but this actually opens a door to some of these studies. And so this is an example of a reinforcement learning agent-based model. This is rendered in NetLogo. You have parameters such as contributors, new maintainers, and a bunch of issue types. So solved, unsolved issues, new maintainers and contributors, which are different types of contributor category. These are individual behaviors. They have motivations and rewards. And then we have all these different issue types, solved and unsolved, and then things like moonshot, Earthshot, and Mars-Jupiter shot issues. And these are just different issues at different levels of complexity. So Earthshot issues are the easiest, the Mars-Jupiter shot issues are the hardest. And this relies on group behaviors where there's both coordination between agents and common practices that have to be adopted. And so this is, again, an example from an ABM agent. Say there's an agent that's involved in the community. They have a reward structure. The rewards are from just staying a contributor to being a maintainer. The reward signal may be stronger for being a maintainer. This signal also involves learning and leadership opportunities. So being a maintainer isn't just automatically rewarded. It's contingent upon some of the other opportunities in the community. And then ultimately this gets bootstrapped to either maintaining a contributor, losing a contributor, or promoting them to a maintainer. And then finally, we move to cybernetic Big Five personality theory. This is based on the work of de Jong in Journal of Research in Personality. And so personality traits refer to individual differences between these agents and the variation mechanisms. So individuals are represented by valences, which you have positive and negative affinities, and their characteristic adaptations, goals, interpretations, and strategies. And the idea is that we have these different personality types, and some of them have positive valences and some of them negative valences. So for example, when you have orange 3B and you're partnered with cyan 2A, that's a positive interaction. Whereas orange 3B and yellow 3A would be a negative interaction. The idea is you want to get the positive people with compatible personalities, or those that lead to positive interactions, working together, and those with negative interactions maybe not working together. And so you can filter out your agents or your contributors based on these personality types. And so you can at least get some optimization in terms of working groups, who works well together, who doesn't work well together, and so forth. And this is based on personality theory. So there are other factors that may impact their ability to cooperate that aren't really taken into account here. But it does serve as a nice balance to some of the things with respect to active inference and reinforcement learning. And so attractive interaction in the agent-based model world is affinity based on a shared working style. So we'll consider a shared working style. This is the agent-based model. It's set up, it's ready to go, and you see that there are two green agents that are together in space. And so there's a positive interaction there between green and green. And that's an example of how you get these working groups where people are working close together. There's also the potential for repulsive interactions, disaffinity based on conflicting work style. And you can see here that the red and the orange are repulsive, so they don't cluster together in space. And so this is a guide to how these personality types might cluster. So you see these big green clusters at the top of this image in the simulation, where you get these very tightly knit working groups. Whereas if you bring together people with repulsive personalities, they won't work together. And so what do conflicting and shared working styles look like? Sometimes this is purely about personality. So it could be about their personality type. But sometimes you get conflicting tasks, you get uncoordinated scheduling conflicts, and you get cooperative tasks, which draw out these distinctions in personality. So if you maybe have two people working casually together, they might get along, but when they need to do something really intensely coordinated, they cannot do it. And so this is why this is important to model this and make sure that we understand the relationships between specific types of personalities and the community. And so a community manager might take a personality inventory of their community, plug it into one of these models, and see what that structure should look like. And so the future directions, we want to sort of map this to the idea of the ethical good regulator. And so this is from Mick Ashby's work on ethical regulators and super ethical systems. He proposes a bunch of different very large-scale variables for the ethical regulator, that you have a lot of things going into it: intelligence, variety, truth, purpose, ethics, predictability. They go into this ethically regulated system, and then there's awareness, which serves as a feedback loop. Now, we could actually redraw this ethical regulator based on this work to redefine some of these variables and show how these interactions happen. And so we can map it, particularly the active inference model and the reinforcement learning model, to this model of ethical regulation. We can also look at reflective equilibrium, which is from a different work from Awad et al., computational ethics, which is in trends in cognitive science. They talk about reflective equilibrium, which is this sort of computational ethics approach where you have intuitions which generalize to principles, and then it get applied to use cases which get tested against moral intuitions. And some of that is reflected in the personality simulations, although there's some work to be done in expanding this out to match the current literature. And some of this also has to do with forking, licensing, and training open source generative AI, in the sense that we can get a sense of how those interactions might be optimized by looking at these different factors in these open source communities. So in generative AI, there's a lot of forking of platforms. There's a lot of licensing issues where there's conflict between, what do I do in terms of not violating intellectual property rights, but also training my model? How do I fork a model responsibly and not, try to replicate other people's work or use it for nefarious purposes? So we can actually use these type of approaches in terms of ethical regulation to solve some of these problems. And so coming soon, we have a sustainability auditing tool, which is a web interface that would allow community managers to go in and test their information about their community against these different models, and then come up with an ethical set of guidelines or a sustainable set of guidelines for their community. And then beyond this sort of sustainability simulation is systems design. So how do we design the most sustainable open source communities and organizations? Mick Ashby provides this diagram of super ethical system design. And so, we use this as sort of an inspiration for where we take our work next. Thank you for your attention. We have a preprint on this work now available on ResearchGate.